Hey everyone, welcome to this video. Let's talk about deep reinforcement learning. So in the previous video, we talked about Q learning, where after training, we get an optimal Q function, which gives an optimal Q table, which gives an optimal policy, and that gives optimal actions to maximize rewards. In reinforcement learning, the model learns through actions within an environment and receiving a positive or negative reward for its actions. In short, the model learns through trial and error. However, reinforcement learning does not need weights, which we have been learning about in this AI in deep learning course. Although we will soon learn how weights slash neural networks can be used in reinforcement learning. And in a simple game like move a stick figure around in a grid with very few states, such as the position of the stick figure, we have not had any issues with Q learning. But what if the game becomes much more complex, like a 3D game, as we can see in this image, and has many more possible states? If the number of possible states and actions is large enough, using a table for representation will no longer be efficient or work well. So instead of a Q table, let's use a neural network which uses weights to calculate the Q value, the expected future rewards for an action in that state. So here we have two different neural networks we could use. And the obvious question is, which one should we use? In the long run, both of these give the same results. For example, let's say we have three actions. The diagram on the left will call the model 3 times. The diagram on the right will call the model 1 time, but gives 3 outputs. Let's use the neural network or the diagram on the right because calling the model 1 time instead of 3 times will be less computationally expensive. So for the Q function, we no longer use this Q table. Instead, we use a neural network with weights. And deep Q learning, step 1 is initialize Q values. 2, take an action. 3, enter a new state. 4, measure the reward. And then update the weights of the model so it predicts better Q values. And repeat steps 2 to 4 as needed. And using both reinforcement learning and neural networks together has led to great performance in a model being able to play video games. But there's going to be some issues with Q learning slash deep Q learning. Remember that a policy is like the agent's brain slash decision maker. Tells the agent what action to perform in a state, and we want a good policy that gives good actions to maximize rewards. In Q learning slash deep Q learning, we will try to calculate the value for a given state in action. We then get our policy through choosing the action with the highest value. But because Q learning slash deep Q learning gives a value for every action, it becomes more difficult if we have a high number of possible actions, e.g., a lot more possible actions than just left, right, up, and down that we had when trying to move a stick figure in a grid. It also becomes more difficult if we have a continuous action space, which means an infinite action space, such as turn right 40 degrees, turn right 40.01 degrees, turn right 40.02 degrees. So one solution some of you might have thought of could be bucketing, where for a continuous slash infinite action space, you could use bucketing to limit the number of possible actions. E.g., you tell the model to only calculate the Q values for whole numbers, such as turn right 40 degrees, turn right 41 degrees, turn right 42 degrees. But this bucketing approach may not work all the time. Maybe for turning the steering wheel only 40 degrees or 41 degrees, like whole numbers, it might work for a car. But what if we're trying to turn a vehicle that's really big or really small? Maybe bucketing will only work for some of those approaches. I hope that makes sense. Like, bucketing can be a solution, but it may not work all of the time. So what could we do? Well, anyways, going back a little bit, what are the issues with Q learning slash deep Q learning? Because Q learning slash deep Q learning gives a value for every action, it can handle smaller action spaces, such as the environment on the left, where there is a grid and you can only move left, right, up, and down. but it will have much more difficulty for continuous slash infinite action spaces, such as the environment on the right, where you can turn right 40 degrees, turn right 40.01 degrees, turn right 40.02 degrees, etc. Enter the policy gradient. We have learned one reinforcement learning algorithm so far, Q-learning. Let's learn another one, policy gradient. In Q-learning slash deep Q-learning, we will try to calculate the value for a given state and action. We then get our policy through choosing the action with the highest value. Now, instead of learning a Q function that gives Q values for every possible action, policy gradients will learn the policy directly. So, what does learning a policy directly look like? It will be the policy giving a probability distribution for the actions available for a given state, so that actions that maximize rewards over time are very likely to be picked. So in this diagram, let's pretend that this triangle is like a drone we are controlling, and we want it to fly around this big red X and fly off into the sunset. But if it hits this red X, the drone crashes and gets damaged. So we want to go to the right. Notice that for policy gradients, the neural network no longer gives Q values, instead gives probabilities. And the model thinks with 98% probability that moving to the right is the ideal action. Okay, we see policy gradient works when we have a limited number of actions, which is left, right, up, and down, just 4 actions. But what about continuous slash infinite action spaces? For continuous slash infinite action spaces, sample from the probability distribution, which is the policy output, to get an action. So in this diagram, the drone is at this point of the sky or space, and what do we want to do? Should it go to the left or keep going to the right? Hopefully, we want the drone to keep going to the right, because if it goes to the left, it'll crash into the red X. And here, this probability distribution or policy output has a very small chance of turning to the left and a very big chance of turning to the right. And we pick a point in it, it says turn right 40.01 degrees. In short, the model is essentially saying the ideal action is whatever action is sampled from the probability distribution, rather than an infinite amount of numbers or Q values for infinite actions. We can instead just use 2 numbers, mean and standard deviation, to create the probability distribution that we will sample from. In policy gradient training, 1. Use your policy to finish an episode. 2. Compute the rewards over time. 3. Update model weights to increase probability of sampling actions for high rewards over time, and to decrease probability of sampling actions for low rewards over time. That's a mouthful. What is this essentially saying? Well, in this episode, the drone flies to the left and hits the red X and crashes. That's not good. Let's decrease the probability of going to the left and then increase the probability of going to the right. This is better, but it still crashes. So what do we want to do? Increase the probability even more of going to the right. And now our drone flies to the right more and is safe and sound. All right, so quick comparison of Q-learning to policy gradients. In Q-learning, you learn a Q function and you take an action by using the highest Q value, whereas with policy gradients, you learn the policy directly and you take an action by sampling from the policy output, a probability distribution. And we have gone over a lot of reinforcement learning stuff in the past video or past 2 videos. So let's do a review. In reinforcement learning, the model learns through actions within an environment and receiving a positive or negative reward for its actions. In short, the model learns through trial and error. Reinforcement learning is useful for complex environments with unknown rules, many rules, and or rules with high complexity, such as a self-driving car or a robotic arm. In Q learning, after training, we get an optimal Q function that gives an optimal Q table, that gives an optimal policy, that gives optimal actions to maximize rewards. However, if the number of possible states and actions is large enough, using a table for representation will no longer be efficient or work well. And that's where deep Q learning comes in. Instead of a Q table, let's use a neural network which uses weights to calculate the Q value, the expected future rewards for an action in that state. And in policy gradient, we learn the policy directly, and a massive benefit to that is we can handle continuous / infinite action spaces, or when we have just a lot of possible actions in general. Okay, that's it for this video. Thanks for watching.